So, okay, that's expectation, okay? Another thing that we can look at is variance, okay? Now, we've looked at variance before, haven't we? Looked at variance before. It's associated with what? Yes, spread, exactly. So how spread out your data is. In fact, it's also associated with standard deviation, yeah? What's standard deviation then? Can somebody remind me? Sorry? Good, so it's the square root of the variance, square root of the variance. But what actually is standard deviation? What's it measuring? Go on, Hoja. Good, exactly. It's the average distance from the mean. Do we remember that? So standard deviation is literally telling you what is the average distance that values are away from the mean. Okay? Good. So we can still work with variance with probability data as well. In other words, how much spread do we expect in this data? Okay? Just remind me, can I rub this off the board now? Yeah, this blue bit off the board. Just remind me, if I was working with data, so sample data, how would I work out variance? How would I work? What's the formula for working out variance? Can anybody remember? Good, or mu, whatever, yeah? All squared. Perfect. Yeah? You happy with that? Yeah, you recognize that formula? Okay. This is if it's sample data. If you have the full population data, it's just divided by 1. It's just divided by n. But let's suppose we've got sample data. It doesn't really matter in this case. Okay, so look at the screen for me. Okay. This is the formula which you should remember. So I've used mu. Let's suppose we're working with sample data. Let's go x bar. Sample data x bar. Let's keep it consistent. Okay. Now, we need to think about this. Now we're working with probabilities, aren't we? We're working with probabilities. So does the sample size, does n, matter anymore? Does it make sense? Not really, because we're working with probabilities. We said this right at the very start. Now we've got this probability distribution. Excuse me for a second. Go away. Okay, now we're working with probability distributions. Are you happy that the n doesn't make sense anymore? Because we don't know what the sample size is. We just have the outcomes and their associated probability. So actually, we may as well rule that off now. We don't care about that. So we just need to work with this. Okay? So here we go. What I'm literally saying now then, is that variance should be this kind of idea, but multiplied by their associated probability. Does that make sense? Similar kind of idea to what we were doing over here, right? When we were just taking the mean of something, we took each individual outcome, multiplied by its associated probability. But now when we're working with variance, instead of working with the distance between the expected value and the current value, the outcome squared, we need to multiply that by its associated probability because it's the chance of it coming up. Does that kind of make sense intuitively? Yeah? So literally just following the idea of variance, you just use that idea and you just multiply by its associated probability. Same kind of idea as this. Is that okay? Yeah? So therefore then, could you try and work out the standard deviation for me? Could you try and work out the standard deviation? Just using that idea there. So by the way, we also give this a symbol sigma squared. That's fine. So we can write it as sigma squared, or we can write it as the variance of x. Okay? Okay. Okay, that's fine. Cool. Okay, so hopefully you should have something that looks like this. You can see all I'm literally doing is for each individual outcome, I'm taking this, I'm taking away the mean, I'm taking away 0.92, I'm squaring all of that, I'm squaring it, and timesing it by its associated probability. I'm doing that for every single one, and I'm just adding them all together. Do you see that? Yeah? And what do we get, Oilam? If we did that for the variance? Oh, because you used 0.97. That's fine. Just give me the number which you got then. Okay, so you might get a slightly different answer to this. I just want a number. Okay, so it'd be somewhere close to that. Okay, because I think Oilam adjusted this for the case that we're rounding in here. That's fine. Okay, so we get 1.498. If we want to work out the standard deviation, okay, it'd just be the square root of the variance. So square root of this, what do we get, Oilam? 1.2247. Like this. Okay. Okay, so once you find this, same idea to find the standard deviation, just to find the square root of it. Okay. So let's think about what that means. Okay. We said expectation, 0.92. We said expectation. If somebody was to walk through that door, pick somebody at random, we would expect them to find somebody who had a number of siblings of 0.92. Okay. What does this mean? 1.2247, the standard deviation. What does that mean? Perfect. So if you didn't catch that, because this is a really important idea, can I ask you to have your attention for a little bit? Okay. This here is your standard deviation. So we said with the expectation, if you were going to select somebody at random, you would expect them to have 0.92 siblings. But would you expect them to have exactly 0.92 siblings? No, absolutely not. Right? We wouldn't expect them to have exactly 0.92 siblings. We would expect them to have it within some certain range though. So it's likely that the number of siblings they have would be within about 1.2-ish of 0.92. Okay? So in other words, the number of siblings, we can do this on a sort of number line. Okay? The expected number of siblings would be here at 0.92. And either it could be 1.2 in that way, so the standard deviation in that way, or 1.2 in that way. So within that kind of range, that's actually realistically the expectation. Okay? So the expectation, if you remember, is just one number, but you need to understand the spread of the data as well. So spread of the data is about 1.2. So in actual fact, you expect somebody to have a number of siblings within that range. Does that make sense?